Okay, now let me explain Frank Starling law, cardiac work, and Laplace's law because they are so important, specifically in clinic and diseases, and also and treatment of different types of disease. Now, first of all, about Frank Starling law, then we will talk about these curves. Okay, this gentleman and this law of this gentleman tells us that this is a heart. Okay, this is a heart. It tells us that the more you put blood volume or end diastolic volume, the more you will get cardiac output or stroke volume. It means when you full left ventricles more, okay, it will give you more cardiac output or stroke volume. Okay, but in physiological limit. Okay, if you furthermore full ventricles from the blood, a time will reach that cardiac output and stroke volume drops. Okay, come here to explain you. For example, normally in normal situation, this very important law. Okay, specifically in heart failure. Okay, why in heart failure? In heart failure, we have a lot of blood volume inside the ventricles, but the cardiac output is less, the ejection fraction is less, the stroke volume is less. Come here to the normal situation. For example, this is Z line, okay, or Z disc. Mhm. I'm talking about contractile unit of myocardium. These two rays are thin filaments. Okay, I've explained all of them in histology of the cardiac myocytes. And this one is thick filament. Now, in normal situation, listen me carefully. In normal situation, for example, this is thick filament. This is thin filament. Here, this is one head of myosin. This is another head of myosin. This is another head. We have three heads of myosin here, three here. So in a nutshell, we have six heads of myosin. Here, these are the active sites. These are active sites, active sites, active sites of thin filament. So when head of myosin joins to the active site of thin filament, it causes cross bridge and it causes contraction of the myocardium. Okay, so now in normal situation, in normal healthy situation, now one head of myosin plus two head of myosin. This is an example. Two head of myosins are joined to these two active sites of thin filament. Okay, so as a collectively two here plus two here, as a collectively four head of myosins cause cross bridge in this contractile machine. Okay, now come here to this second one. Now I'm going to put a bit more blood volume, which Frank Sterling law explains that the more you put, the more you will take, or the more you will gain cardiac output. Now in this second situation, come here. In first situation, this one, this active side in this active side, or as a collectively these four active sites were free. Okay, so these active sites were free. Now when I stretch it, when I stretch myocardium, it means I stretch out this contractile machine. So when I stretch out, now three head of myosins join to three active sites. Okay, so here in first one, four here, for example, 2 plus 2 4 4 plus 4 8 head of myosin cast contraction. Here now we saturated all active sites of thin filament by head of myosins. So as a collectively six here, as a collectively 12 head of myosins work together and they cause contraction. Okay, so this contraction is stronger than this contraction, like Frank Sterling law. But now, when you put furthermore volume, okay, now the cardiac output drops. Come here, come here. For example, now when I stretch out, For example, when I put cardiac output, so myocardium stretches. So when I stretch out myocardium, furthermore, come here, it means I'm stretching these two Z lines or these conjunctile filaments from each other. Now here, come here, in this situation, now these two active sites are free now. And only one side of thin filament is saturated by this head of myosin. So this one side produces weak contraction compared to this 16 side, compared to these 16 sides. Okay, so that's why here contraction gets weak, and due to weak contraction, heart ejects less blood volume. That's why if you stretch out myocardium or you put more volume, it causes depletion and reduction of cardiac output. Got it? So this is about Frank Starling law. Okay. For example, here in graph, this is end diastolic volume. Okay. For example, the volume when we put here on the walls of myocardium or inside the ventricles. Okay, so this is also called end diastolic volume. Now listen me carefully. If you increase the end diastolic volume, the cardiac output increases, but a time will reach that when you increase the end diastolic volume, I'm going to this side, when you increase the end diastolic volume, cardiac output drops. Got it? This is Frank Starling law. Okay, and also I'll talk here about these parameters also. Okay, now here, come here, this is very important. Okay, because Laplace's law, Laplace is this another gentleman, it tells us here is a thing. Okay, it tells us that tension is equal to radius times pressure, and tension is directly proportional to work, and work is directly proportional to oxygen consumption. It means when you increase the tension in the wall of myocardium, the work increases, the oxygen demands increases, and when you don't supply oxygen to the myocardium, so heart is going to ischemic heart disease. Okay, so now tension is equal to radius times pressure. Now come here to this curve. Okay, that's why this is important. For example, I'll talk furthermore under the title of cardiac work later on, don't worry. Now in this direction, in this x-axis, we have left ventricular volume. In this direction, we have left ventricular pressure. I'm not talking about systolic and diastolic pressure or the pressure which is inside the aorta. I'm talking about the pressure which is inside the ventricle and volume which is inside the ventricle. And also, I'm talking about left side of the heart. Now, it explains us that when you put more volume, okay, like this, okay, so easy. For example, when you put more volume during diastole, this curve is for diastole. Okay, diastolic curve. Okay, now when you put more volume during diastole, listen me carefully, up to 130 or 150, there will be no tension, there will be no pressure on these myocardium. But when you increase the volume more than 150, so suddenly this curve rises. Okay, and this is diastolic pressure, this is diastolic pressure. So when you put furthermore blood, then 150 ml, then 200, then 250, then 300. So because heart cannot stretch furthermore, heart has a fibrous connective tissue around it, heart has a pericardium around it, so it cannot stretch furthermore. So this wall of the myocardium feels tension, so the pressure inside the ventricle rises, it rises furthermore it rises. For example, in normal situation, the pressure during diastole is so less, it's around 70, 80. For example, when you increase it, so pressure rises. Okay, so this is very dangerous, because when you increase the pressure, based on Laplace's law, when you increase the pressure, you increase the tension on the walls of ventricles. When you increase the tension, you increase cardiac work and you increase oxygen demand, and it will cause heart failure plus ischemic heart disease. Come here about systolic. It's like Laplace's law, okay? Well, it's like Frank Sterling law. It says that when you increase the volume, the heart will stretch a bit more and it will contract stronger than previous, and systolic pressure increase. A time will reach that when you increase the blood volume more than 250 or 300 ml, systolic pressure drops. Okay, when it drops, it means now you cannot pump blood from the ventricles. So this curve is called left ventricular pressure, left ventricular volume pressure curve. Got it? And heart is normally functioning in this area. Okay, I'll explain it here, only in this area. Now come to this graph, and then we will talk about cardiac work. Okay, now, okay, first of all, I'll explain cardiac work, then I'll talk about this one, okay, to know it better. Now come here to cardiac work. Okay, first of all, come here about the work. Let me explain you work clearly. Okay, work. What do I mean about the work? I'm not talking about physically, but anyway, in physics, work means that work is equal to distance times force. For example, I'm pushing a wall. Okay, if I can't displace this wall, so it means I didn't perform any work. Okay, so, and when you displace a thing from one area to another area, it means you did a work. So, okay, so work is equal to distance times force. Okay, force means how much energy is produced by you, and that's why work is directly proportional to work is in body, in our heart, work is directly proportional to oxygen consumption, and oxygen consumption is directly proportional to ADP. So when you increase the cardiac work, it means you increase the ADP and oxygen consumption by the heart, okay, or you increase demand of the heart, because an ischemic heart disease, this ischemic heart disease, in ischemic heart disease, okay, there is two problem. One problem is that sometimes demand increases and sometimes supply decreases to the heart. So imbalance between the demand and supply causes ischemic heart disease. Okay, so come here, I'll explain it clearly. Now, in our body, distance is equal to blood volume, the volume which is ejected by the heart. For example, this is our heart. When it ejects blood, it displaces blood from this area to this area. So physiologists cannot measure the distance here. So instead of distance, this is the amount of blood which is ejected by the heart. This is equal to distance. Okay, the volume. And now, when we eject volume in one beat, this is called stroke volume. Sometimes this is also called stroke work. Okay, an amount of blood which is ejected by the heart, this is called cardiac output. So sometime this is also called cardiac output, is also called minute work. It means amount of work which is done by the heart in 1 minute. Got it? So now here, very easy. Okay, don't worry. Now about force. Okay, this is classical classification. I'll talk about new classification also. Okay, now about force. Force here is the pressure which is generated by the heart against the total peripheral resistance. Okay, for example, during normal situation, heart generates pressure around 120. During systole and during diastole, the pressure here will be around 80 millimeter mercury. So when I take the main pressure of these two, which is called main arterial pressure, it is equal to 93. I'm not talking about types of pressure, we'll talk about the pressure in upcoming video lecture. But when a person has 120 per 80 millimeter Eg pressure, so the main arterial pressure will be 93 millimeter Eg in that person. So here, come here. Force here is equal to pressure, which is generated by the heart, and the pressure here, which is equal to the force. This is mean arterial pressure. This is main arterial pressure. So this part in classical definition and in classical classification, this part of the heart, which is distance equal to volume to stroke volume, this is sometimes called volume work, and this part is called pressure work. Okay, i'll explain it I'll explain it now. Okay, that pressure work uses more energy than volume work. Okay, why? What do I mean by this? For example, I have a heart. This is a heart of a normal person. It pumps 5 liter blood in 1 minute. Okay, in 1 minute. In how much time? In 1 minute, by how much pressure? By 120 millimeter Eg pressure. Here is another person who is exercising. So during exercising, that person ejects around for example 15 liters blood in 1 minute by this 120 millimeter by this 120 millimeter Eg pressure, or by 130 millimeter Eg pressure. So now who is healthy physiologically, okay, you will never see that person in a gym that he goes to ischemic heart disease, that he produces ischemic heart disease. Okay, because when your heart ejects a lot of blood, it does not uses a lot of energy. But for example, here I have another patient, okay, which has mitral stenosis. Now, in mitral stenosis, because I have stenosis, so in 1 minute, cardiac output drops to 4.5 liter. But pressure increases because now heart pumps against a strong resistance, which is stenosis here. So the pressure increases up to 180, up to 190, up to 170. Now this patient can go to ischemic heart disease. Okay, this patient can enter to ischemic heart disease, but that person who produced a lot of blood volume, he will never enter to the ischemic heart disease. So that is the proof that this is because this is pressure. So pressure work uses more energy. But in new guideline, this is so easy. Now this is as a collectively that we have cardiac work, okay, which is made of distance times forces. But they divided cardiac work into two parts. They divided the cardiac work into external work and into potential work. External work means that amount of blood which is ejected by the heart plus plus the pressure which is generated by the heart, as a collectively, both of them are called external work. And potential work means, for example, when heart contracts, so now it contracts, it does not eject all blood from the left ventricle. Amount of blood which remains inside the left ventricle, it's called end systolic volume. So now before it ejects all blood from the heart, the heart goes to relaxation, okay, to diastole. So let heart contracts like a spring, okay. When you release, it produces a force during diastole, and this storage energy inside the ventricle walls during systole, this energy is called potential work. So it means that during cardiac work, the most energy is used by the external work of the heart. So now come here, this is so easy. Come here, we have a curve here. This is related to the left ventricle volume and pressure. Okay, now this is left ventricle volume, this is left ventricle pressure. So now it's so easy. Okay, now here this is volume of the left ventricle. So I have already 50 mLs of blood in ventricles always, okay, which is in systolic volume. So I'll start from this point. Now I'm in this point, okay. So now atria contracts, okay. When atria contracts, in this all phases, in this filling phase of ventricles, during filling phase of ventricles, this valve, I'm talking about left side of the heart, this valve which is called mitral valve, this is open in this phase, in rapid ventricular filling phase, in slow ventricular filling phase, and all phases. So it means during diastole of the heart, the mitral valve is open. So now this is the mitral valve in a point, it's open. Now I'm going from 50 ml to 70 to 90 to 100 to 120 in all these phases. I reached 120 ml, which is called end diastolic volume. So now when atria, okay, here this atrial contraction, after atrial contraction, isovolemic isovolemic contraction occurs. So in isovolemic contraction, atria produces a lot of pressure. Now listen me carefully. In this phase, which valve is closed? Now mitral valve is closed. Now mitral valve is closed. Here mitral valve was open. Here mitral valve is closed. Okay. So now this pressure will be developed. So this is left intraventricular pressure. This is left ventricular volume. So now listen me carefully. A load of pressure will be produced here up to one, up to 90 or 80, and around 80, a valve will be opened by this pressure, which is called aortic valve. So now this is open. Okay, and a lot of blood is ejected from the heart. Listen me carefully. Pressure develops from 80 up to 120, up to 120. So pressure goes up, but volume decreases. Volume from 120 comes back to 50. So here, when I reach to a pressure, okay, again, which is around 80, so this valve is closing, which is aortic valve, and again pressure drops inside the ventricle, and there is no volume change. Here is also no volume change. Here is also no volume change. Here ventricles is during filling, and here ventricle is during emptying. Okay, so now I come back to this phase. So now all this area, all this shaded area, all this is called as a collectively external work. Pressure plus volume, all of them are called external work. So most of the energy which is used in a cardiac work, it's used in this place, in this area, which is external work, which is made of pressure plus volume work together. Got it? And here, which I talked before, that here between pressure work and volume work, the most energy is used by this point, from point B to point C, this A point, B point, C, and D. Okay, because here heart generates a lot of pressure. But anyway, all of this is called and into external work. Okay, and here this area is potential work. Okay, which does not use a lot of energy. Got it? And this blood which is ejected by the heart, this is called stroke volume. Also, yep, we did a lot about Frank Starling law, about cardiac work. Now this is so easy. Laplace's law. Laplace says that in left ventricle, inside the left ventricle, this is the wall of the left ventricle. When you stretch it, okay, or when you contract it, so there will be a tension, and a tension will be produced inside the wall. So this tension is equal to, we have different types of Laplace's law. Okay, but here I'm not talking about the pressure, which is pressure equal to tension times 2 divided per radius. I'm not talking about that. I'm talking about the tension in the wall of the left ventricle. Tension is equal to radius, this is the radius, okay, times pressure. Okay, now here listen carefully. when you increase the radius, for example, in heart failure, you are going to put more blood here. Listen me carefully. You are going to put more blood volume. You increases you increase the tension in the wall of the left ventricle, and this, when you increase the tension, when you increase sorry, when you put a lot of blood inside the ventricle, it means you increase the radius. Okay, when you increase the radius, it means you increase the tension. Okay, plus sometimes when heart contracts, okay, against high pressure, so against high pressure, the heart produces a lot of pressure. So when you increase pressure, so it means you increase tension. So in both condition, when you increase the radius or you increase the pressure, you are going to increase tension, and tension is directly proportional to cardiac work. It means you are going to increase cardiac work, because when you dilate the heart, it provides a lot of energy, it produces a lot of energy, it uses a lot of energy for contraction. So you are going to increase cardiac work. And when you pump against high total peripheral resistance, you are going to produce a lot of pressure. So this pressure also increases cardiac work, and when you increase the cardiac work, you are going to increase ADP usage, you are going to increase oxygen demand. And when, now in this time, when you don't have enough supply to the heart, so you are entering to the less energy state in the myocardium, and myocardium is entering to a phase which is called ischemic heart disease. Okay, so these laws are so important in treatment of different diseases like ischemic heart disease, like heart failure, and so on. So these were all about the cardiac cycle, about different phases of cardiac cycle. We talked about parameters, we talked about phases of cardiac cycle, we talked about pressure and volume, because we talked about cardiac work and oxygen consumption, we talked about Laplace's law, we talked about Frank Sterling law, and we talked about the uh, controlling of heart. We talked in previous lecture that how sympathetic and parasympathetic nervous system affect the heart. Okay, we talked about these sympathetic and parasympathetic nervous systems completely about in under the title of rhythmical excitation of the heart. Okay, and then guided and health physiology. At the end of this chapter, we have some things that effects of calcium on heart, effects on potassium on heart, effects on for example, a heat on the heart. Okay, we will discuss these things under the titles of hypercalcemia in internal medicine. Okay, don't think much about these things. Okay, and there is no clinical point much here, and have a good time till next lecture.